Well, hello. Welcome to a brave new year, I guess you could say, that we're looking at. And what we're going to be doing today is looking at beginning our AP Physics learning from a distance here. And one thing I'd ask you to do is take notes on this. It might seem a little odd to take notes when you've got a presentation in front of you, but there's a lot of research that would go into saying that the very act of writing down notes by hand, just the act of doing that actually helps improve memory and kind of sets it in. So I'm going to ask you to take notes along the way here. So if you don't have a notebook on ready or standby, just kind of pause the recording and get that. And what we're going to talk about today involves kinematics. Okay. Now, what is kinematics? And you've seen the word kinetics before in terms of kinetic energy and whatnot. It basically means motion. And when I say 1D, I'm talking about one-dimensional. So my wife sometimes describes my personality as being one-dimensional, but I think that's a little bit cruel. But one-dimensional motion just implies that your motion is limited either along the X or Y axis. Now, we're not always going to limit ourselves to that. We're going to get to two-dimensional motion here in a second. Not in a second, in a couple days here. But we will not get to three-dimensional motion where we're dealing with both X, Y, and Z planes. We're just going to deal with two dimensions, and that's going to be enough for us. So we're going to limit ourselves either to traveling along the X or the Y axis here. So when we do this, a couple things to mention here is that we are going to be working mostly with, let's bring this puppy down here a little bit further. I don't want you guys to see everything. So we're going to be comparing the idea between distance and displacement. You notice I put a little bit of an asterisk there. That's for the fact that we are going to try to emphasize displacement rather than distance. And you might ask yourself, well, what the heck's the difference, Mr. Lizzie? Well, that's what I'm here to explain. Well, for one thing, distance is what we are going to describe as being a scalar, and displacement is going to be what we would call a vector. And again, notice that I'm trying to emphasize in bold right here that we're going to try to focus on vectors here because we need to incorporate the idea of direction. A scalar is going to use only the magnitude of that measurement, whereas a displacement is going to include both the magnitude and the direction. So, for instance, a magnitude might be 60 kilometers, where a vector would be 60 kilometers to the east or to the north or what have you. Those are vectors. Vectors are going to include a direction and a magnitude. So when we describe a displacement, we're always going to use the formula x sub f minus x sub o, or basically my final displacement in the x, or it could be y, direction versus my initial displacement or my initial position on the x-axis there. So always take final minus the initial. And the zero there basically represents at time zero. So in order to determine displacement, we're always going to take our final minus initial. That will give our signage the correct values there. So we are going to assume that positive displacements are going to be up, so a positive y. East is going to be a positive displacement, and to the right is going to be a positive displacement. And negative displacements are going to be down in the negative y. West is going to be a negative displacement, and to the left is going to be a negative displacement. Okay. Now, let's contrast a distance versus a displacement here. So if I were to swim a lap in a pool, if that were the case, I'm going to swim here, in this case, to the right. That's going to be a positive displacement, and to the left. Now, in this case, my distance that I travel is going to be, let's say, 50 meters, because it would be 25 meters this way, 25 meters back. That would be a distance. But my displacement would actually be 0, because my final position is exactly the same as my initial position. So if that's the case, let's say I travel this 50 meters in, let's say, 50 seconds. Okay, so if that were the case, my speed would be 1 meter per second, but my displacement, since my displacement is 0, my velocity would actually be 0. And that's what we're going to get to in terms of the difference between speed and velocity. So hopefully that clarifies that a little bit. And again, we're going to focus on the idea of displacement rather than distance. It's going to be much more helpful to us. So I kind of let the cat out of the bag here a little bit because we're going to be talking about speed versus velocity. And again, trying to emphasize we're going to focus on velocity here rather than speed. And just as before, we're going to just kind of start building our knowledge here. Speed is going to be a distance divided by time. Velocity is going to be a displacement divided by a time. And when we do this, our normal SI unit, our International System of Units, is going to be meters per second. Now, the problem that I'm going to solve for you today is not going to use meters per second, but in general, that's going to be our default. We're going to try to avoid the feet per second or miles per hour. We're going to try to keep it in these SI units. And so we're going to abbreviate our SI units as being meters per second there. And we can do that anytime you can cut some time off with the abbreviation, we're going to do it. So we're going to talk about a little bit about velocity here. And what we're going to start doing is building what I would describe as being your toolbox. It's going to be a toolbox of equations because what we're going to need is we're going to need to grab the right tool for the job. Okay, I'm not going to use a hammer to try to unscrew a screw. I'm not going to use a C-clamp to screw in a screw. Okay, I'm going to use the right tool for the right job. I'm going to use the right equation for the problem that's necessary. So what I would recommend you doing is find some part of your notebook and reserve maybe 5 to 10 pages. That's going to be a little bit extreme, but I want to make sure you have plenty of room to write down all the equations we're going to be using this year. And that way you have an easy reference point for them at all times, and it will help you considerably when you try to solve these problems. So the very first equation that we're going to give you, you should know that kind of our displacement is going to be that x final minus x initial. Okay, our first equation, and again it's going to seem a little bit simplistic here, but it's going to be this idea of I don't think I'm doing this correctly. Oh no, we're doing it correctly. Is going to be the idea of displacement divided by time. So our x final minus our x initial, that's going to be our displacement. Our time is going to be that. So we can shorthand that into saying that that is delta x, x final minus x initial is our delta x, divided by t, or delta t. So that's going to be our velocity. But the nice thing is that we can use a little bit of algebraic juggling, and we can actually get 3 equations for the price of 1, which is going to be pretty handy for us. So just as velocity equals delta x divided by t, I can rearrange this, multiply through by time, and get the fact that delta x equals velocity times time. Or, conversely, I can take, now that I've got this equation, I can divide by velocity and say that my time is going to equal delta x divided by my velocity there. And again, we're going to keep it in our SI units when we solve this. So what I'm going to do is I'm going to throw one demonstration problem at you, and then you are going to have time to kind of practice on your own and kind of let me know whether or not you have some issues with that. So one thing I'd recommend is going through a habit of solving these problems. A lot of times people get lost because physics is more of an art. We're actually in some ways doing the same problem all year long. We're just writing down what the problem is giving us and employing the equations that we have in order to solve it. And one little kind of handy tool that I would recommend you thinking about is try to keep this acronym in mind. Don't guess. We're going to try to create a paper trail because then it's easy for us to see where mistakes are made. And it's also easy on the AP exam for the scorer to see, okay, they knew this problem up to a certain point, and I can give them some credit for that. So what does the D mean? The D means the very first thing you're going to do is when you read a word problem is you're going to diagram that situation. There's my D. Okay. The G stands for what is the problem giving you? Okay. Write down, they're labeling some values. What is the problem giving you? Sometimes they'll give you extraneous information, which isn't very handy. We can isolate what's important. Unknown, what is the problem looking for? That's what the problem is asking. What equation am I going to need to solve the unknown? And quite frankly, guys, if you get to this point, you've won the game. If you can figure out the right equation to solve it, the rest is just kind of crunching numbers. You could get a well-trained chimp to plug quarters into a vending machine beyond that point. Okay, if you have the equation down many times on the AP Physics test, that's all they'll ask you for is the equation. What equation would you need to solve it? They very rarely deal with numbers. They just deal with the values. And the S stands for substitute. Let me move this red line here out of the way. Okay, you're going to substitute in your givens into the equation, and then you should be able to solve that. Okay, so when you do that, that's kind of what we're looking for. Let me get that out of the way there. Okay, so when you answer, make sure you include both the magnitude and the direction on your answers there if necessary, okay, for these types of problems. So let's look at what this might look like. You've got two boats that start together and race across a 60-kilometer wide lake, and then they race back. Boat A goes across at 60 kilometers per hour, returns at 60 kilometers per hour. Boat B goes across at 30 kilometers per hour and back at 90 kilometers per hour. So the problem is which boat wins and by how much. Now, most of you guys, I'm sure you could crunch this out, hot dog it, figure it out within a couple seconds, but that's not the point. The point is that we are going to face much, much more difficult problems in this, and we're going to need a system to solve it. So let me show you kind of the system. It's going to seem a little bit arduous and time taking for this type of problem, but it's going to be helpful to develop a method that's going to help us out later on. Okay, which boat wins and by how much? What's the average velocity of the winning boat? We'll only worry about this first part right now. Okay, but we should be able to figure that out. The average velocity of the winning boat is going to be 0 because it ends up back where it started from. We already saw that. So here are a couple boats. There's boat A, goes across a 60-kilometer wide lake. Okay, I'm diagramming it out. Boat B also goes across a 60-kilometer wide lake. That's my diagram. I want to picture this situation. If I can visualize it, it's going to be much more helpful for me. So the next thing I'm going to do is I'm going to write down my givens. Okay, what is my velocity of boat A? Well, it's 60 kilometers per hour this way, 60 kilometers per hour back. That's what the problem would suggest. Okay. Boat B travels at 30 kilometers per hour on the way there, 90 kilometers on the way back. Now, the clever among you would recognize that, hey, by the time boat B gets all the way across, boat A is already back home. But that's great that you know that, but let's work through the process here. So my unknown, okay, here's my distance. My delta x1 is 60 kilometers. My delta x2 is also 60 kilometers. I've got all of these problems were given to me in the initial word problem, all these givens. So my unknown, how much time does it take for boat A? How much time does it take for boat B? And what is the difference in time? Which boat wins and by how much? And we could reverse these. It doesn't matter. We don't know which boat wins at this point. But we do know that this will give us some value, and we can just figure out what the time is for each one. So my equation that I'm going to need here, I'm starting to run out of time, is delta x1 plus delta x2 divided by VA. My time for boat B is delta x1 divided by the velocity of boat 1 plus x2 divided by the velocity of boat 2. I could put a delta x in front there, I probably should have, but time constraints and whatnot. So these are my two equations. That's going to help me solve that. Okay. All I did is I rearranged my toolbox equations a little bit here. I had to do some manipulating to do that. I'm going to substitute in. What do I know? I know delta x1, delta x2, and I know the velocity. For boat B, I know my delta x1, I know my delta x2, and I know the velocities of each. And as a result, I should be able to solve those problems. And there's my answer.